Hi, my name is Julian Gordon. I go by Alex, and I'm interested in mentoring a chemistry course at UNC this following spring semester. So I think I'd make an excellent candidate for a number of reasons. To begin with, I consider myself qualified in this subject material. Um, and all the chemistry courses I've taken at UNC so far, I've gotten A's, which goes to show not only how I'm passionate about the subject, but also the extent to which I'm willing to put in work to learn the subject as much as I can. The second primary reason I consider myself qualified and a good candidate is because I'm really interested in teaching people. I've found myself numerous times in the past in a position in which I'm teaching my peers the material, and I'm really enjoying doing so, and I find it really personally fulfilling to help people understand the material better. Um, and for that reason, more so than the former, I'd really like the opportunity to be able to teach UNC students the course material that I myself struggled with um, just a few months ago. Um, and it's for those reasons that I consider myself qualified, and I would really enjoy the opportunity to mentor a chemistry course at UNC. So, without further ado, I'll show you how I would go about solving a potential acid-base titration problem for a student of mine.
So you'll have to excuse my recording abilities. I don't really have a whole lot of equipment, so sorry for all that. Anyway, I'll be solving this problem as if I were to be describing it to a student of mine. So here it goes. Here we have 100 milliliters of 0.1 molar glycine hydrochloride solution, and it's being titrated with 40 milliliters of 0.2 molar potassium hydroxide. What is the pH of the final solution? And you have the pKa's for glycine hydrochloride being 2.34 and 9.6. So the important thing, probably the first step to do here would be to identify what you're actually working with, which would be potassium hydroxide, which is a strong base, and glycine hydrochloride, which is a weak acid. We know potassium hydroxide is a strong base simply because it's part of that list, magnesium hydroxide, sodium hydroxide, those kinds of things that we are expected to memorize early in Gen Chem. And we know glycine hydrochloride is a weak acid simply because it is not one of the strong acids and strong bases we were expected to memorize. Therefore, by default, it is a weak acid or base. We know it's an acid because it is fully protonated, so it's a weak acid, which we'll abbreviate as GH for the time being. Anyway, so you have potassium hydroxide, strong base, reacting completely with glycine hydrochloride. Now, I say it's reacting completely because, well, what differentiates a strong acid from a strong base? That would be the ability of the strong acid, what differentiates a strong acid and base from a weak acid and base? Well, the strong ones dissociate completely, and they also react to completion. So however many moles, however much potassium hydroxide strong base you have, that's the extent to which the reaction will proceed. Whereas weak acids and bases don't dissociate completely. So in this case, you'll have potassium hydroxide dissociating into potassium and hydroxide ions in a aqueous solution in water. And this hydroxide here will go on to essentially deprotonate a hydrogen ion from an acid, in this case a weak acid, signified as HA, to form water and the acid's conjugate base, which is signified by A minus. And I should be review, but A minus HA used to signify complementary weak acids and weak bases. A complementary acid-base pair is simply a compound that has varying degrees of protonation that are differentiated as relatively acidic and basic. So for example, H2A could be deprotonated to HA minus, could be deprotonated to A2 minus, which is actually exactly what's happening here, as you can see by the two pKa's. So the first pKa governs this one. Second pKa governs this one. So that's what's actually happening here, is this potassium hydroxide is driving this reaction to completion. It is fully neutralizing the weak acid here into its complementary weak base pair, weak base alternative. So the first step in actually solving the problem, now that we know the principle of what's actually happening here, is finding how many moles of each compound we have. So we know we have 0.1 molar of GH, glycine hydrochloride, divided by 1,000 milliliters in a liter, and times 40 milliliters. And that's going to be equal, I'm sorry, that's times 100 milliliters, isn't it? Times 100 milliliters, which ultimately equals 0.01 moles. Conversely, we have a 0.2 molar potassium hydroxide solution divided by 1,000 milliliters times 40 milliliters, which is going to equal 0.008 moles of potassium hydroxide. A little barrier there. That's how many moles of each we have. So you'll notice that we actually have fewer moles of strong base than we do of weak acid. What does that mean? Well, that means that we're ultimately going to produce this many moles of weak base from this weak acid, but no more, no less, only 0.008, because we know that for every mole of hydroxide produced, we're creating 1 mole of weak base. Therefore, we're going to have 0.008 moles of weak base, since potassium hydroxide converts weak acid into weak base. So we know 0.008 moles of weak base is produced, and since you started with 0.01 moles of this weak acid, that leaves us with 0.002 moles of weak acid, of original weak acid left. Technically, since it's polyprotic, it should probably be more like H2A and HA minus, but as long as we understand the concepts behind that, that's all that really matters. What does this leave us with? Well, as we should know, whenever we have a complementary acid-base pair in solution, it creates a buffer. And as also we should have learned, we begin to associate the word buffer with the Henderson-Hasselbalch equation. The Henderson-Hasselbalch equation is to be used whenever you have a buffer in solution and you want to actually assess the pH of that buffer, or assess any of the other variables included in a Henderson-Hasselbalch equation, which is as follows. pH is equal to pKa plus log base over acid. Base over acid is usually the safest to do in moles, since concentration can often vary as you include more and more of something, but you can also do concentration if you're willing to put in the work for that. In this case, we'll just keep it to moles since we already figured out what that is. From here on, it should be relatively simplistic. So we have pH, which we're trying to find, and that's going to be equal to the pKa, which is 2.34 in this case, since, as I've said, it's a polyprotic acid, which means that you have your starting material here. Let's just kind of imagine it's there, H2A, being deprotonated into its intermediate form of HA minus via pKa1, 2.34. If you were to start with the intermediate form and add potassium hydroxide to that, then you would use 9.6, because that would be the pKa governing that particular reaction. In this case, it's governed by 2.34 because it's starting way over here in a fully protonated form, and this is the first pKa. That's the first extent to which a fully protonated acid is in equilibrium. We start with 2.34 plus log and we just fill it in with these two variables we found here. 0.008 divided by 0.002. And from there on, we just use our calculator to do 0.008 divided by 0.002. The log of that, 4.60205. And we simply add that to 2.34 to make pH equal to 2.94. As always with pH calculations, we do it to 2 sig figs. Or 2 decimal places, I should say. And that is how we solve that particular equation. Thank you so much for listening.